So if not, let's continue with our discussion on chapter 2, which is focusing on linear time-invariant systems. Okay, so at the end of chapter 1, we talked about various properties of systems, and among them, linear and time-invariant are two of the most important properties that we will focus on throughout this course. So this is because if you're looking at systems that are linear and time invariant, it allows us to simplify the analysis much more, right? Making the analysis much more tractable while still being able to analyze systems sufficiently accurate, for most cases, right? So the reason that this makes our life easier, which will also be clear later on, is because if you're looking at linear systems, then they satisfy the so-called superposition property, which means that if you insert a superposition of multiple signals at the input, then the output will also be the superposition of their corresponding responses. Okay, so this is the advantage that linear systems give us. And secondly, if the system is also time invariant, this means that no matter when the input arrives, the response will take on the exact same shape except for a corresponding delay. Okay, so linear allows us to utilize the superposition property, and time invariance allows us to deal with the same shape of a unit impulse response, except for a certain delay corresponding to the input. Okay, and these two properties will become clear in a moment. Okay, so to fully utilize these two properties, right? Let's start out with the discussions out with discrete time discrete time signals. Okay, so to fully utilize these properties, it's important to view discrete time signals as a sum of shifted and scaled unit impulses. Okay, it's a sum of shifted and scaled unit impulses. So what does this mean, right? So for example, suppose you have a signal like this, right? So suppose that this is the signal xn that we're interested in, okay? So you can see that, xn, right, is basically a superposition or a sum of all these values at different time instants, okay? And each one of these can be viewed as a unit impulse at the corresponding time, scaled by the value of the function at that time. Right? So for example, this point here, right, can be viewed as this impulse function, this impulse unit impulse function, right? This sample here can be viewed as this unit impulse, this one as this, right? This one as this, and this one as this, right? So this shows us that, for any discrete time signal, we can always, view it, or we can basically split it up into these scaled and time-shifted impulse function, right? One corresponding to each sample at a different time instant. Okay. Now, for a sample at time -2, right, this is expressed as delta of n plus 2, right? This delta function or unit impulse shifted to time -2, scaled by the value of x at that time. Okay. And the impulse at time -1 is delta of n plus 1 times the value of x at that time, and so on and so forth. Okay. So for any signal x event, you can write it as the summation of all these time-shifted and scaled impulses. Or more concisely, you can write them as the summation of xk delta of n minus k. Okay? Okay, and this is for k from minus infinity up to infinity. Right? Now this equality here, right, x of n equal to summation of xk delta of n minus k, is also what we call the sifting property of a delta function. Okay, so the reason this is called a sifting property is because, if you multiply the sequence x with the unit impulse at time, this unit impulse, right, shifted to time n, then you're basically sifting out the value of the sequence at time n. Okay, so this is why this is called the sifting property. So we actually used this property before. If you recall in chapter 1, right, when we looked at the unit step function. Okay, so suppose that you substitute, unit step function into as the signal x here, then un should be equal to summation uk delta of n minus k, k from minus infinity to infinity. Okay, but the unit step function is equal to 1 for k greater or equal to 0 and 0 in an entire negative axis. So in this case, I can actually limit the summation for k from 0 to infinity of these delta functions of n minus k. Okay? All right. So if you recall, in chapter 1, we showed that the unit impulse, the unit step function, you can write as the summation of these unit impulses at times 0, 1, 2, 3, 4, so on and so forth. Okay, and you can view this equality as a consequence of this sifting property we mentioned above. Okay, so do we have any questions about this? Do you have any questions about this? Okay. So basically, what we're saying here is that for any discrete time signal, we can view it as a superposition of these unit impulses at different time instants. Okay. Now, if the system is linear, then the response of this linear system, would then be the superposition of the scaled responses of these, time-shifted impulses. Okay, so we viewed the input xn as a superposition of these time-shifted impulses. So then the response, right, the output to the system, must then be the superposition of the responses of each individual time-shifted impulse. Okay. So mathematically, what this is saying is that, suppose that HKN is the response that you get if you insert a impulse at time k at the input. Okay, so suppose that HKN is the response that you get if you insert a impulse at time k at the input. Okay, so this is saying that, suppose you have this linear system, and if you insert a unit impulse at time k, then your output would have a response HKN. HKN. Okay. So here you have a few examples, right? So for example, this H sub minus 1n is the impulse, is the response that you get if you insert a impulse at time -1 at the input. Okay. Now, if you insert a impulse at time 0, then you would get a response H0n, which looks like this. And if you insert a impulse at time 1, then you would get a response H sub 1n, which looks something like this. Okay. So inserting a impulse at different time instants in general will give you different, responses at the output. Okay. Now, we mentioned previously that for any discrete time signal xn, right, we can represent it as a superposition of these time-shifted impulse functions. Okay. Right. So xn, right, any discrete time signal can be viewed as a superposition of these unit impulses, right, at different time instants, right, and the coefficients of this superposition is given by xk. So if the input is a superposition of these unit impulse functions, then by the linear property, the output of xn, let's denote by yn, should also be a linear combination or superposition of the corresponding responses of these unit impulses. Okay. So do we have any questions? Let's see.那个林佑伦在吗？
有。
对，这边有没有什么问题？
没有问题。
没有问题。OK， 所以就是说，可不可以稍微用你的话，就是讲一下说为什么这个 xn 的 output 就是可以写成这一页里面的这个式子。
因为那个 delta 的 n 减 k 是跟 hkn 是 linear 的，然后就是 delta n 减 k 跟 hkn 是 linear 的，然后所以我们的 xn 可以写作这一个形式这样。
OK， 所以我想可能意思上稍微比较不一样，就是说，其实我们现在是系统是 linear 的，我们系统是 linear 的，那HKN 是 delta n 减 k， 就是我如果输入 delta n 减 k 的话，我的 output 就会是 HKN 这样。那之所以可以写成这样，是因为就是说由于我的系统是 linear 的，所以我如果 input 是一个 superposition of 一些 function 的话， 那么它的 output 就会是同样的这个 superposition of 这个每一个 input 所对应到的 output 这样子。OK， 好，谢谢。再问一下这个黄亮轩在哪？这个黄亮轩在吗？那卢瑞斌呢？
有，
对这边有没有什么问题？对这样的一个 superposition 的特性？
没有。
没有。OK， 好 ，OK， 好，因为这个地方这个概念是还蛮重要，所以希望确认大家都有了解这样子。OK， all right, so again, if a system is linear, right? This is only true if a system is linear, right? The output of a signal would just be a superposition of the corresponding responses of these time-shifted unit impulses. Okay? All right. So on the next page, we have a simple example, right? So suppose that we have a signal xn that is equal to, something like this, right? So you have values at -1, 0, and 1, and 0 everywhere else. Okay. So you can view xn as the sum of these three time-shifted and scaled unit impulses. Okay. So xn is basically, the sum of this plus this plus this to get this xn signal here. Okay. Now, previously, we know that delta, a unit impulse at time -1, will produce an output h sub -1 of n, okay, scaled by the same value, x of -1. And x0 times the delta function at time 0 will give you at the output, the response h sub 0 of n times the scale x of 0. And similarly for impulse at time 1. Okay. So if the input is a superposition of these three time-shifted impulse functions, then the output will also be the superposition of their corresponding responses. Okay, so the output should be the sum of these three, okay, to get this function yn here. Right? Okay, so this is when the system is linear. Okay. Now, if you further know that the system is also time invariant, okay, then you can further simplify this expression a little bit, because for time invariant systems, the responses to time-shifted unit impulses are also time-shifted versions of each other. Okay, so this is saying that if you have two unit impulses inserted at different time, then the output will take on the same shape except for a corresponding delay. All right. Okay. So for example, suppose that Okay, suppose that you have a linear time-invariant system here. Okay, and you insert a impulse at time 0. Okay, you insert a impulse at time 0. So this is delta n. All right. So, and then for this unit impulse, you observe at the output a response that looks something like this. Okay, so assuming that this is time 0, 1, 2, 3, and so on. Okay, so this response we call h sub 0 of n. Okay. Now suppose you instead, insert a impulse at, let's say, time k. Okay. So suppose that this is delta of n minus k, right? So if the system is time invariant, what do you expect to see at the output? Okay. 来问一下同学，那个温成凯吗？是这样念吗？这个温成凯同学在吗？温成凯同学在吗？还是这个钟汉文同学在吗？
在。
那就是对于一个 input， 就是一个这个时间 k 来的一个 impulse delta of n 减 k， 你预期它的 output 会是长什么样子？如果系统是 time invariant 的话
output 也是 h 去，然后时间也在 n 减 k。
可以再说一次吗？
input 是 delta n 减 k 嘛？那 output 也是 output 就会变成 h， 然后 n 减 k。
就是跟上面的 h 一样，但是 n 减 k，right？
对对对，它会平移一样的位移。
OK， 谢谢，对，非常好。OK， 所以 so for this delta n minus k, right? The output would look exactly the same as h sub 0 of n, but time shifted to time k, right? So suppose that this is k, then I would get something that looks like this. Okay. All right, so this we can denote by, okay, so suppose we define this as hn, then we can write this as hkn equal to h of n minus k. Okay, so hkn is the response to a unit impulse at time k, and it is just a time-shifted version of the impulse response corresponding to an impulse at time 0. Okay, so this is basically what's mentioned here, right? So suppose that this hkn is the response to a impulse at time k. Okay, and if the system is time invariant, then hkn will just be a time-shifted version of the response corresponding to a impulse at time 0. Okay. All right. So if you substitute hkn equal to h of n minus k into our equation before, right? So if you substitute that into this equation here, you find that yn can be written as summation x of k times h of n minus k, okay? So this is a superposition of this time-shifted unit impulse responses, right? Okay, so this impulse response corresponding to a impulse at time 0, we call the unit impulse response, okay? So yn is just a superposition of time-shifted versions of these unit impulse responses scaled by the value of x at the corresponding time instant. Okay. Now, this is what we call a convolution sum, or sometimes called a superposition sum. Okay. And for such a operation, we denote it by x of n with a star or asterisk in between h of n. Okay. So this notation here represents what we call the convolution of two sequences x of n and h of n. Okay. And the operation is given by this convolution sum here. All right. Now, if you look at this expression, you will see that, given the unit impulse response Hn, we will be able to derive the output to any possible input xn, right, if the system is linear and time invariant. Okay, so again, this equation tells us that, if you are given h of n, the unit impulse response, then you can completely characterize the output for any input xn, right, if the system is linear and time invariant. So this is saying that this unit impulse response Hn completely characterizes a linear time invariant system. Okay, so this is a very important remark. Right, so an LTI system is completely characterized by its unit impulse response, Hn. Okay. So to describe a linear time invariant system, right, basically meaning that to characterize, the input-output relation of a linear time invariant system, it is sufficient to specify what is the unit impulse response, H of n. Okay. Now let's look at a few examples of this, convolutional relationship.